31 is about Maxwell's equations, and Maxwell's equations summarize all of electromagnetic theory very much the way that Newton's equations can summarize mechanics. Newton didn't originally come up with all three of his laws. He took other people's work and compiled it, but he said these three laws explain motion. Okay. That's what James Maxwell did. He said that there's four equations that summarize all of electromagnetic theory. The first one, let me go ahead and find it. Maxwell lived from 1831 to 1879, to just give you a little perspective. And his four equations are these. The integral over a closed surface of E dot dA is equal to the charge enclosed over epsilon naught. We studied that as Gauss's law. And that was back in chapter 22. His second equation says the integral of a magnetic field dot dA is equal to 0. That's called Gauss's law for magnetism. And that's actually introduced in this chapter 31. I'll be honest, I don't know that Gauss wrote this law. I'd have to look that up. But it's a parallel situation with this same logic. The difference being that since magnetic fields form closed loops, if I have a closed surface like this, picture a spherically closed surface, magnetic field lines never stop. And so inevitably, the magnetic flux into the surface has to equal the magnetic flux out of the surface. That's different than for electricity, because electric field lines actually originate on charges. So it's possible, you can picture a sphere around this, you'd have lots of lines passing through the surface. But notice these are all going out. So with an electric field, if you have an enclosed charge, you will have, this product will equal that enclosed charge. But with a magnetic field, it always equals 0. So that's the second law. The third law says the integral of an electric field times E dot dl. So we're going to make a closed loop, not a closed surface. This is linear, that's an area. A closed loop is equal to negative d phi dt. It's equal to the rate of change of the flux. This is Faraday's law. It's the general form of Faraday's law. We just looked at Faraday's law in chapter 29. And then finally, the fourth one says that the closed integral of B dot dl is equal to mu naught I. Now that's not the whole formula. That's what we studied as Ampere's law. And that tells you that the dot product of a magnetic field over a closed loop is equal to mu naught times that enclosed current. And that's true as long as you do not have a changing electric field. If you have a fixed electric field, you don't have anything changing. But what they found is that it didn't explain everything. If you want to have a deeper understanding, you can go and look at chapter 31 in the first section, section 1 and 2, I believe, and they'll go into a bit of a deeper explanation. But Maxwell, this is his big contribution, said there is a second term when there is a changing electric field. And this is the generalized form of Ampere's law. It's not the one the way we studied it in chapter 29. It's a more complete version. So we have these four laws. Notice they're all written in integral form. There's also versions of these laws that are written as differential equations. Differential equations are even a higher level math than just integrals. So this is probably the simplest. So hopefully you've got those written down. They're certainly in your textbook in chapter 31, beginning at section 3. I want to give just a brief explanation of each one and what they say. Or what they represent. Okay. The first one, Gauss's law, is a generalized version or let's say generalized form. I like that better. Of Coulomb's law. Relating electric fields to electric charges. We might think of Coulomb's law relating force to electric charges, but in this more general form of Gauss's law, we're actually relating the electric field, E dot dA, to electric charges. Okay. So that's what Gauss's law says, and that's what Gauss's law does. Gauss's law for magnetism states that since there are no magnetic monopoles, we know there are no magnetic monopoles, or if we find them, we're going to be rewriting electromagnetic theory. That means magnetic field lines are continuous. They form those closed loops we've talked about. The result of that is the number of lines. And when I talk about lines, I'm talking about magnetic field lines or lines of flux entering a closed surface. Equals the number of lines exiting. Okay. Then for any closed surface, because those magnetic field lines form closed loops, no matter how we draw it, the number of magnetic fields and lines that are entering that surface will equal the number of lines exiting. Hence, we get that integral of B dot dA has to equal 0. That's the law for magnetism. So that's an easy one. law is Faraday's law. We just finished studying Faraday's law. And Faraday's law just says an electric field, and you can think of this as meaning an induced EMF. And an EMF is something that exerts a force or a pressure on electric charges. That's what an electric field does. Is produced by a changing magnetic field. A constant magnetic field does not produce electricity. It will not induce an electric field. It won't cause a current to flow. But we know a changing magnetic field will. And finally, our fourth one says that a magnetic field can be produced two ways. Magnetic field is produced by a current. That's the original form of Ampere's law that says the integral of B dot dl equals mu naught I, where I is the enclosed force, but there's more to it. Or by a changing electric field. And that's this second term that says mu naught epsilon naught times the rate of change of the electric flux, d phi dt. Take this one more step. Let's go on into section 31-5. So that was that was chapter 31, section 3. Let's look at chapter 31, section 5. -5 deals with the topic of electromagnetic waves. From this point on, I'll just use a capital EM because I'm not going to write electromagnetic that many times. If I think about a region of free space, I'm in free space, which is sort of a physics phrase for I'm out there in a vacuum somewhere. And in this location, there are no charges, or currents. What's that mean? That means Q is equal to I is equal to 0. Those things do not exist. So if I'm out in free space somewhere, Maxwell's equations get real simple. The first one, E dot dA, will equal 0 because there's no charge. And this one, E dot dL, will equal negative change in flux. Okay. That's Faraday's law right there. The second one, the one for magnetism, already equaled 0. And the fourth one, since there's no current, looks like this. the bottom two that are really interesting. What this is saying is if I have a changing magnetic field, I'm going to have an electric field. I'm going to changing magnetic field, I'm going to have an electric field. And this one says if I have a changing electric field, I'm going to have a magnetic field. So we get into this cyclical thing with electromagnetism that once started, a changing magnetic field will induce an electric field. And that electric field won't be constant because the magnetic field is changing. So we get a changing magnetic field causes a changing electric field or a time-varying electric field. And a time-varying electric field induces a time-varying magnetic field. And we know a time-varying magnetic field induces a time-varying electric field. And a time-varying electric field induces a time-varying magnetic field. What we end up with is a self-propagating electromagnetic wave. Let's draw a picture of it, and let's look at the math that we often use to talk about it. If I draw a picture of it, we start with a three-dimensional axis. There's a y-axis, here's an x-axis, here's a z-axis. I'm going to get some different colors because that'll be helpful here. If I let the electric field be on this y-axis, then it will look like a sinusoidal wave, just like every other sinusoidal wave we've ever gone. We'll call this maximum value E0. Okay. In the field, we know the electric field and the magnetic field have to be perpendicular to one another. So the magnetic field we would be drawing on the z-axis. And it would look something like this. It would be, if this is in the xy plane, the magnetic field is in the xz plane. It's a little harder to draw, but it would look something like this. Now again, I'm trying to draw this one going. So if the electric field is oscillating vertically like this, the magnetic field would be oscillating horizontally like this. Okay. There is a right-hand rule. If you take your right hand and you put your fingers in the direction of the electric field, you have to be able to rotate toward the magnetic field, E cross B, and it will give you the direction of the velocity of the wave, which I've drawn this way. So we have a case here where our wave is propagating in the positive x direction. Okay. Now, in reality, most electromagnetic waves or sources of light have their electric field oriented in all directions, not just vertically in the y direction. But the magnetic field associated with that electromagnetic component is always perpendicular to it. E and B are always going to be perpendicular. The velocity will be perpendicular to the both of them. These have the exact same wave equations we studied back when we studied mechanical waves. The electric field can be represented, or the displacement, as both a function of x and t. In this case, it's strictly in the y direction just because that's how I drew it. And it would equal E0 sine. You can tell we've drawn it as a sine wave. Maximum amplitude is E0. Kx minus omega t. K is going to equal 2 pi over the wavelength. That's called the wave number. Omega is called the angular frequency. It's 2 pi f. Or it could be written as 2 pi over the period. We usually think of it as angular frequency as 2 pi f, but that is, we know that f and t are reciprocals. The magnetic field associated looks exactly the same. It is also a function, but in this case, the magnetic field is in the z direction. It is equal to V0 sine kx minus omega t. So our equations that represent the electric field and the magnetic field look just exactly like our other wave equations, where the displacement at any point is a function both of its location x and as the time that's elapsed. If we look at this, we know that the velocity of a wave would be equal to the wavelength divided by the period. If I do this wavelength, if I do this wavelength, it would be 2 pi over k. The period would be 2 pi over omega. If I use the rules I learned from middle school about dividing by fractions, I see that this works out to be omega over k. If we were a little more gifted with our calculus and our mathematics at this point, we might be able to derive what I'm going to give you. It is derived for you in the textbook, so I suggest looking over and reading through. But we gain a couple of really important pieces of information. Maxwell's equations make a prediction that basically say that the speed of the electromagnetic wave should be equal to the ratio of the electric field to the magnetic field. But it also says that speed has to equal, and we call that c. We have in free space, the speed of an electromagnetic wave, c, is equal to 1 over the square root epsilon naught mu naught. And this relationship, then, C is equal to E over B, and C is equal to, has been measured to be So we've got a lot of good formulas. We've got our two wave equations. You need to be comfortable with those. We have our definition for our wave number and for our angular frequency. Like I say, all of this here, I believe you've seen something similar before. What's really and truly fascinating is that Maxwell's equations predicted the value of the speed of light. And at the time when the equations were first understood, we didn't really understand that light was an electromagnetic wave, but it met all these criteria. And so that was one of the big outcomes of if Maxwell's equations are right, then electromagnetic waves should travel at this speed, which coincidentally, when measured, turned out to be the speed of light. And so we understood for the first time, really, that light was an electromagnetic wave. Okay, we'll talk more about electromagnetic waves in the next video.